Good evening, everyone, and welcome to session 23 of S.Eng's training series. And today, Dr. Ghosh will start on the first seismic lecture, and he will be covering earthquakes and the effects on structures. And with this, I will transfer the mic to Dr. Ghosh.
Thank you, Bodhi, and good evening. As Bodhi said, we are starting on the seismic modules. We have 8 of them. The first one today is pretty general. It's earthquakes and their effects on structures. I do not go into detailed uh, design procedure of any kind. That will come in the next few days. This is almost setting the stage for what is to come and to make you familiar with fundamental concepts and things that are always involved in seismic design. So the other segments, I didn't have this lesson objectives, but this particular one, I think we had to put something together for the U.S. military. I don't remember, but when I saw it, I liked it. So I think it will be good to look through it. So upon completing this lesson, just today, participants will recognize the background to the building code seismic provisions, including source, nature, and characteristics of earthquake ground motions, the nature of building response to ground motion, the concepts of frequency, period, damping, resonance, inertia force, and load paths. Those are all, each and every one of them is a very, very important concept. Frequency, period, damping, resonance, inertia force, load path. The concept of inelastic structural response and consequent need for proper detailing. Then seismic force resisting structural systems. Okay. So it is quite a bit. At the same time, I do not have yesterday's situation where we had 150 slides. And so I do not expect to have time problems today. Earthquake ground motion to start with. Most earthquakes, not all, but most, result from a rapid movement along the plane of faults within the Earth's crust. Yeah. Plane of faults. So those are seismic faults that are in many parts of the world. And most earthquakes results from rapid movement along those faults. Sudden movement of fault releases a great deal of energy which travels through the earth in the form of seismic waves. I think that's understandable upon reading. The seismic waves travel to great distances before finally losing most of their energy. Now, how far it travels, etc., depends on the size of the initial break or disturbance, but generally what is said is true. So the source of the earthquake is typically down some distance below the surface of the earth. That point where the earthquake originates is called the focus of the earthquake, and the point vertically up from the focus on the surface of the ground is called epicenter. So you hear about epicenter from the earthquake. Epicenter of an earthquake, it is always on the surface of the of the earth. The focus on the other hand, is down below. There are shallow focus earthquakes, there are deep focus earthquakes. Shallow focus earthquakes, much more common, are much less devastating. The deep focus earthquakes, much less common, can have absolutely devastating effects. The fault is here. This is the fault plane, and there has been a rupture along the faults as indicated by and movement along the fault as indicated by those arrows. The fault rupture has caused seismic waves that are depicted in the picture, and at one point the seismic waves will get to your building, and we have to consider the effects of those on the building when we design the building. This is for a 10-year period. There could be subsequent, but one 10-year is not very different from another 10 years. Seismic activity around the globe. And the main thing you see is that earthquakes happen in some places and not in other places. So this is about the biggest conclusion that emerges from a picture like this. So western part of the United States, plenty of earthquakes. In the east, hardly, and compared to the west, hardly any earthquakes in the east. Okay. The color indicates the depth of the focus. The color that is most common are very shallow focus earthquakes. As you go from that color to this color to green and so forth, you are looking at deeper and deeper focus earthquakes. And you see that shallow focus earthquakes are much more common than deep focus earthquakes. The deepest focus earthquakes in red are few and far between and only in a few parts of the world. Okay? So two things are true. There is no spot on earth where you can say with absolute certainty that there can never be an earthquake here. That cannot be done. The probability of occurrence is very low, but we cannot say with certainty that it cannot happen here. Secondly, the reverse of that is also true, that the probability is way higher in some parts of the world. There is absolutely no question. Okay? So you compare California, let us say, go down to cities. You compare Los Angeles with Chicago. It is not even comparable. Los Angeles has, I don't know how many times higher a probability of having an earthquake within a given time period. The crust of the earth is made up of a number of tectonic plates, as they are called, and those plates are in perpetual motion with respect to one another. And many earthquakes, again, not all, but many earthquakes originate along those tectonic fault plate boundaries. Okay? The movement of one plate with respect to the other generates the earthquakes. Okay? There have been earthquakes smack in the middle of tectonic plates, so I'm not claiming that all earthquakes are at plate boundaries, but the vast majority of them are at plate boundaries. And if you compare the previous picture with this picture, you will kind of see that the preponderance of earthquakes follow the plate boundaries if you look closely. Now, Getting specifically down to Bangladesh, Bangladesh is located in a tectonically active region close to the plate boundaries of the north moving Indian plate and the Eurasian plate uh, to its north and east. This whole thing is Eurasian plate. Okay? So the Indian plate is moving north-northeast. The Eurasian plate is to the north and east of the Indian plate. Lack of earthquake awareness and preparedness may lead to massive disaster if major earthquakes strike. All of this picture and the writing are from Dr. Tahmid Malik Al Husseini of Buet. I took it from a written paper or from the internet. Recent tremors have frequently shaken the southeastern region, as Chittagong. Some have caused damages. Then there is a list of strong earthquake affecting Bangladesh. So 1869 Kachar earthquake, you see magnitude 7.5, which is huge. 1885 Bengal earthquake, magnitude 7. The distances of the epicenter from Dhaka are given. The 1897 Great Indian earthquake, incredible, 8.7, 230 kilometers from Dhaka. 1918 Sri Mongol earthquake, 7.6, and Dhubri earthquake of 1930, 7.1. Now the thing is, the list stops at 1930. So from that point on, from 1930 until today, 91, 92 years have passed without an earthquake of that kind of a size, 7 or 8. Sorry. Moderate damaging earthquakes in Bangladesh in the last 10 years. There's a list. May 1997, magnitude 5.6. November 1997, earthquake at Myanmar border, 6.0. July 99, Moishkali. December of 2001, earthquake near Dhaka. Panic and injuries. It's a small earthquake, but because it was close to the city, there was quite a bit of panic apparently. July of 2003, earthquake in Rangamati, that's magnitude 5.6. This list of moderate earthquakes also stops in 2003. that doesn't necessarily mean anything. On November 26th of 2021, the other day, there was a significant earthquake at Bangladesh-Burma border, magnitude 6.1. I know it was felt in Dhaka. I had no way of adding it to this table, so I kind of left it out. So the list definitely has not stopped. The November of 21, it couldn't be any more recent than that. And magnitude 6.1 is a pretty sizable magnitude. Obviously, it was some distance away, so nothing much happened in Dhaka. Although people felt it. Numerous people have told me that they felt the earthquake. So this is definitely ongoing activity. Now, hazard versus risk. Those terms you will see all over the place. Sometimes they are used synonymously as if they're the same thing. They are not the same thing. Hazard is the potential for ground shaking or something else, a potential for some typically adverse event, something good happening the potential for something good happening is never called a hazard. Okay, it is something bad happening. The potential for that is called hazard. Uh, and one of those bad things could be ground shaking. That would be that would be seismic hazard. The risk, on the other hand, is potential for losses associated with the hazard. If the bad thing that we are talking about happens, then what is the potential for losses in terms of human lives or damaged property or whatever? Okay, that is the risk. So seismic hazard is a matter of uh, geology, the the tectonic environment of where you are, even the history of what has happened in the past, that sort of things. It has absolutely nothing to do with the structures we build or live in and things like that. Seismic risk, on the other hand, is very much dependent upon what we build. If these are flimsy uh, houses, uh, masonry buildings that are not reinforced, etc., the risk to human life and to property is extremely high. If the construction is of high quality, then the risk goes down. The hazard being the same, the risk could be high for poor quality construction and could be low for high quality construction. I think that should be kind of intuitive and obvious. Okay? So hazard and risk are not the same things. At some time after their generation, seismic waves reach the Earth's surface. Remember, they originate always some point below at the focus. At some time after generation, seismic waves reach the Earth's surface and set it in motion, which we refer to as earthquake ground motion. The, the waves traveling along the surface of the Earth. When earthquake ground motion occurs underneath a building, and when it is strong enough, that the ground motion, when the ground motion is strong enough, it sets the building in motion, starting with the building's foundation. That's what happens. An earthquake moves the foundation from underneath the building all of a sudden. And the rest of the building, unless it is a very short, stocky building, cannot readily follow the movement of the foundation. It stays behind and then tries to catch up with the movement of the foundation. That sets the building up in motion. Okay, so the ground motion sets the building in motion, starting with the building's foundation, and transfers the motion throughout the rest of the building in a very complex way. It is the vibration of the building can be quite complex because of what I mentioned. It is that you all of a sudden the foundation starts moving every which way. That's the only way I can say it. That's what happens in an earthquake. It's not that the foundation starts moving from left to right or front to back. No, it's not like that. It starts moving every which way at the same time. And because of inertia, the rest of the building cannot immediately follow the movement of the foundation. So the building stays behind and tries to catch up with the movement of the foundation. That sets the building in motion, which can be quite complex. These motions in turn induce forces that can produce damage. So when a building moves, obviously there are deflections. You take first derivative of deflection, that is velocity, and you take another derivative of the velocity or second derivative of the displacement, you get an acceleration. So when a floor of a building is experiencing deflections because of the motions that we are talking about, there is associated with that deflection a velocity and an acceleration. Acceleration times mass is a force. So there are forces generated as a result of these movements that we are talking about. And the forces obviously can cause damage. Now, you will hear quite a bit about attenuation of ground motion. That is the word that is used. Attenuation basically means dying away of the ground motion. So this is the epicenter of an earthquake. If you look at ground motion close to the epicenter at this point on the surface, the ground motion may look like this. It's high frequency ground motion. The period is very short. Period here will be from 1-0 crossing to an extreme displacement in one direction to an extreme displacement in the other direction back to zero crossing. The time it takes to do that is the frequency. So this is a high frequency short period motion. The duration is not particularly long. If you look at the same earthquake, if you look at the ground motion generated at this hard point on the surface, you will see a very different ground motion. Now, the duration has increased for one thing. The amplitudes are moderated. The high frequency components have died away. What has survived are the low frequency components. The period of the motion has increased if you look at the picture, okay? And the amplitude has decreased. The high amplitude motions, which were also high frequency, have died away. So I think the picture is pretty graphic. So this is near fault ground motion. This is ground motion away from the fault. Very, very typical. Now, the attenuation that we saw in one way in the picture is typically captured by relationships like this. Here, we are plotting peak horizontal acceleration on the y-axis. It doesn't have to be that. It could be another, could be velocity, could be whatever. But peak horizontal acceleration, that's pretty commonly plotted. And on the x-axis is closest horizontal distance from zone of energy released. That nothing in this business is straightforward. So even that distance, there are many definitions. But anyway, it is distance from source, let us say. Okay, for our purposes, that's good enough. So as you move further and further away from source, the peak horizontal acceleration decreases. Okay? The actual points are measured values in a particular earthquake. I don't remember if the earthquake is described here. Here, 1917 Imperial Valley. This is an actual earthquake. Okay, surface magnitude 6.8, local magnitude 6.6. Okay, so in that earthquake, the measured accelerations at various stations, at various distances from the source, are shown by the black dots, and then the dotted lines are kind of curve fitting. And that gives you an idea as to how the in this case, the peak horizontal accelerations caused by the earthquake die away as we move away from the source. Now the the topic that continues to cause a lot of confusion: intensity versus magnitude. Intensity of an earthquake, magnitude of an earthquake. The intensity is qualitative as opposed to quantitative, but widely used. Magnitude, on the other hand, is quantitative. It is also used just as often or more. Now, this page, I think, is extremely important. It comes from Charles Richter, the who devised the Richter scale. It is now called the local magnitude scale. Whatever, Richter magnitude isn't used much anymore. There are other magnitudes that are used, but those are besides the point. This is analogy that he came up with, which is absolutely wonderful in understanding intensity versus magnitude. Seismographs. So when you see graph, it is an instrument. Seismogram would be a plot made by a seismograph. Okay? Seismographs, the instruments that record earthquakes, record waves of disturbance. The word, this itself caused confusion. We talk about earthquake and seismic, and I have even gotten questions. The word seismic, I forgot now, is in Spanish it is el sismo, an earthquake. The Latin and Greek terms are very close to that. The word does not come to me at the moment. And so an earthquake event is also a seismic event. There is absolutely no difference between the two. We use the words interchangeably. Sometimes for variety, we would say earthquake resistant design, and then in the next sentence we will say seismic excitation and things like that. Exactly the same thing. Okay? So seismographs, the instruments that record earthquakes, record waves of disturbance radiated from the earthquake source. Okay? Waves of disturbance. Just as receiving units, radio units, catch radio waves transmitted by broadcasting stations. Okay, Richter's days it was radio, not so much TV, so he used radio, which is totally fine. But let us please understand this, what is being said. So seismographs record waves of disturbance radiated from the earthquake source, just as receiving units catch radio waves transmitted by broadcasting stations. Magnitude can be compared to the power output in kilowatts of a broadcasting station. That's magnitude. Energy released at source in the case of an earthquake. Okay? The power output in kilowatts of a broadcasting station. Local intensity is comparable to the signal strength of a receiver at a given locality. Okay? So it is the signal strength where you are, the intensity. Intensity, like signal strength, drops off with distance from the source. That's easily understandable, right? Close to the broadcasting station, you will catch higher, stronger signal than away from the broadcasting station. So intensity, like signal strength, drops off with distance from the source, although it also depends on local conditions and the pathway from the source to the point of recording. That also has an effect. What the signals are coming through. Are there mountains in between and things like that. Okay? So it is the in the case of an earthquake, magnitude is indicative of the energy released at source. A and all magnitude scales are uh, log scales, logarithmic scales. So a magnitude earthquake means energy released at source is 10 times that of a magnitude 7 earthquake. But that's what magnitude deals with. Okay. Intensity, on the other hand, is what is felt in that earthquake at your particular site. What is felt at your particular site will depend upon definitely the magnitude of the earthquake and other attributes of the earthquake. Was it a strike slip fault, like lateral movement of the fault? How long was the fault movement? How quickly did it take place? Is it a shallow focus earthquake? Is it a deep focus earthquake? All of those factors. The source related factors will determine what your structure feels at your site. But it is also the source to site transmission path. Are the seismic waves coming through mountain ranges or are they coming through alluvia, on riverbeds? Uh, and finally, the site conditions at the site, because if you have rock at your site, there isn't any amplification of the motion that will arrive at the site. But if you have soft soil overlying rock at your site, the uh, ground motion that arrives in the rock at your site will be amplified by the overlying soft soils. So it is the energy released at source and other attributes of the earthquake at source, then the source to site transmission path, and the local conditions at the site, what kind of site soil conditions you have at the site. Very similar to what Richter is saying here. Intensity, like signal strength, drops off with distance from the source, although it also depends on local conditions and the pathway from source to the point of recording. Surprisingly often, I do not know. This is pretty much the rule rather than the exception. People, including sometimes journalists, will use the expression, this building was designed to withstand a magnitude 8 earthquake. That is a nonsensical sentence, doesn't mean anything. Absolutely nothing. Magnitude 8 earthquake where? If it is a magnitude 8 earthquake next door, it is one thing. If it is a magnitude 8 earthquake 1,000 miles away, then it can be a very flimsy structure. So, we have designed our structure to withstand a magnitude 8 earthquake is a sentence that doesn't mean anything. You have to specify a magnitude earthquake on such and such fault. And then it begins to mean something. there is other. So this magnitude, what it is, needs to be understood. Anyway, let's go through the next couple of. So the earthquake intensity, not the magnitude, is subjective. It is valuable for historic analysis. For real old earthquakes, we do not have the sizes and so forth recorded, but we have a pretty good idea of the damage that was caused, and so uh, we can assign intensities to those earthquakes, and that kind of historic analysis typically proves to be quite valuable. The earthquake intensity varies with construction types, as I explained already, varies with distance and ground conditions, as I explained also already, includes construction type and ground effects. This is the modified Marcelli scale that is used in many parts of the world, not all by any means. In Japan, they have their own scale, and there are others that are Russians typically don't use what is used in other places. So anyway, but modified Marcelli is used in most of the Western world, including the US. So the intensity goes from 1 to 12. 1 to 7 is an earthquake not felt. That's 1. 2, an earthquake that is felt by all with some damage to ordinary and substandard structures. That would be intensity 7. 8 and 9, some to considerable damage to even specially designed structures. So from 8, intensity 8, you are looking at substantive damage. 10 is most masonry and frame structures destroyed, rails bent, landslides, ground badly cracked, and so forth. 11 and 12 are pretty rare, but you can read this. So 1 through 12 is the modified Marcelli scale. From 7 or 8, you are looking at damage, meaningful damage. When you are at 9 or 10, it is pretty serious business that you are talking about. Magnitude is quantitative. It is based on, it is calculated from the size of wave recorded on a seismograph. This is how magnitudes are determined. We look at the records made by seismographs, and from those ground motion records, the amplitudes, let us say, of the motion, we calculate the magnitude of the earthquake. It is a log scale, as I mentioned to you already, correlates with energy released at source. That's very important. There are many magnitude scales. These days, this so-called moment magnitude is what is preferred, but the Richter or local magnitude, surface wave magnitude, body wave magnitude, all of those are in use. And agencies like U.S. Geological Survey, for the same earthquake, will give you 3, 4 different magnitudes, okay? Different scales, I mean. So, and each of them is defined. I will not go into that, but each magnitude, moment magnitude, Richter magnitude defined, all of them are derived from the record of an earthquake on an accelerogram, as we call it, or the records that from seismographs. Let me put it that way. So geological factors affecting ground motion at a site. I have already indicated is the source mechanism. That's the best way to put it. Not just energy released, but as I mentioned, the how deep the focus is, what is the size of fault rupture, what kind of rupture, how quickly it happened, all of those things. Source mechanism, all those things determine the ground motion affecting a particular site. Transmission path from source to site, I have talked about it, and local site conditions. Okay, so the role of overlying soil. You have ground motion uh, in rock, and there is stuff overlying rock. This is soil. This is something in between rock and soil. And what is the difference between ground motion in rock and what is and the ground motion at the surface? And this is what is shown here schematically, obviously. Okay. So at point A, this is the uh, accelerogram, the history of acceleration, variation of acceleration with time. And at point B on the surface, this is the accelerogram. You can see that the soft soil overlying rock amplifies ground motion. Okay, this is stronger ground motion, lengthens the duration, also very importantly changes the frequency content. Okay, so frequency I mentioned, so period would be from 1 0 crossing to one extreme to the next extreme to the next 0 crossing. So from here to there, the time taken is the period. Reciprocal of that is the frequency. Okay, so if you look at the two different motions, the frequencies, now a ground motion typically does not have one frequency. It has a frequency content, a mixture of frequencies. And if you look at the top and the bottom figures, you will see that the mixture of frequencies are quite different between the two. So the frequency content changes because of the overlying soils. Okay. Now, this is a very important figure historically, I would say, because the seismic design we are doing today, dates back to a document called ATC3 that was issued in 1978. There was definitely seismic design before that, but the ATC3 document and successor documents have rewritten the seismic design in many ways. And the how do I want to put it? The way we considered the seismic input in seismic design, the ground motion part, how we considered the ground motion part in seismic design essentially dates back to this figure that Professor Harry Seed of Berkeley put together. I don't remember the year. This was, I should have looked it up. This was in the 70s or 80s. I tend to think it was 70s. Would have been early 80s, that kind of time frame. At that time, this is something that is pretty unbelievable to somebody like me. These days, there is any earthquake anywhere uh, around the globe, we get records of ground motion within definitely an hour or two, sent to our computers totally unsolicited. I got day before yesterday, I think, ground motion from an earthquake in Taiwan that I had no idea had even happened. when a significant event happens, we actually drown in ground motion. So much comes out, so much is recorded. It's unbelievable. But when Professor Harry Seed did his work, there were only his entire work that you see on this slide was based on 104 strong motion records. That's all that was available at that time. 104 actual strong motion records beyond a certain threshold. Now, 30 or so were on rock. 30 or so were on stiff side conditions as he described them. Another 30 or so deep cohesionless soil, and about 15 of the records were on soft to medium clay or sand. What he has plotted is spectral acceleration against period. This would be an acceleration response spectrum, as we would call it. Okay? The spectral acceleration is normalized with respect to the maximum ground acceleration. Okay? So we have numbers on the y-axis. Spectral acceleration, I will talk in detail about response spectrum, I think on the in the last seismic module, anyway, in one of the modules. But for now, spectral acceleration is like maximum acceleration of elastic single degree of freedom systems with varying periods. It is very close to that. It is not exactly that, but for your basic understanding, that's good enough. Spectral acceleration is very close to
Raghu's, you can unmute yourself. I just muted you because there was some disturbance.
okay. Uh, so spectral acceleration, think of it as maximum acceleration of elastic single degree of freedom systems with varying periods. Okay, and we will refine that on a subsequent occasion. Anyway, the figure shows very conclusively that from rock to steep soil, there is an amplification, like the accelerations are higher. As you go from stiff side conditions to deep cohesionless soil, the amplification is even higher. And look at real soft soil. I mean, the comparison between this and that, you can see that the accelerations have increased by a factor of 3 or so. Okay, so there is amplification of in this case acceleration at a site because of soft soils. Now this was driven home to us in a very loud way in the 1989 San Francisco area earthquake, the Loma Prieta earthquake as it is called. That was the last significant earthquake in San Francisco. We have been lucky for it for a long time. There hasn't been any. Anyway, so 1989 Loma Prieta earthquake. This is an acceleration spectrum plotted at Treasure Island, which is on soft soil. And this is in the same earthquake, an acceleration spectrum plotted at Yorba Buena Island, which is on rock. So this is rock motion. This is motion on soft soil. And you see the difference with your own eyes. There is tremendous amplification because of soft soil. If we divide this by that, which is what has been done here. This is the spectral acceleration on soft soil divided by spectral acceleration on rock. Look at the numbers. We have amplification approaching 5. Okay, so this side effect cannot be can not only not be ignored, it better be taken very seriously. Okay, so it is the source mechanism, the source to site transmission path, but also the local site conditions, extremely important. Okay, now the ground motion at a particular site. This is so this 1940 El Centro earthquake, obviously very old. The earthquake was called the Imperial Valley earthquake. El Centro is a place in California, Arizona border area. El Centro, California, a very small place where there is a recording station. So this is a record of the 1940 Imperial Valley earthquake at the El Centro station. That's what it means. Okay. The instruments that make these records, Richter called them seismographs. They're typically called accelerographs. And the records that are produced are accelerograms because these instruments record ground acceleration in 3 mutually orthogonal directions. It would be 2 perpendicular horizontal directions and the vertical directions. So you will get 3 plots of acceleration. Please make sure you follow me. So an accelerograph will give you 3 plots. All 3 are of ground acceleration. Two of the plots are horizontal accelerations in mutually perpendicular directions. And the third plot will be a plot of vertical accelerations. Okay, this is what we typically get out of an accelerograph. The accelerogram at the top is for the north-south component of the El Centro record. There were 3 records. We are taking one of them. This is the north-south, one of the horizontal components. Okay. This one has been used in analytical work for all these intervening years, 80 years or so, with all kinds of accelerograms available today. People still go back quite often to this one because then you can compare with older studies and so forth. So this is still anyway. So if you look at the accelerogram, I think the only thing you can the only word that describes it is erratic. It's erratic back and forth motion of the ground. Okay, so there is really not a lot of pattern to it, except that it goes up and down. Okay, so the acceleration increases, it decreases. Now, agencies like U.S. Geological Survey, who record these things, also would integrate this acceleration history with respect to time, and that gives us a velocity plot. So this is ground acceleration actually measured. This is ground velocity derived by integration from the ground acceleration plot. You see a dramatic change. The period of ground motion, the period of the velocity plot is much longer than the period of the accelerations. The accelerations go back and forth very frequently. The velocities do not go back and forth anywhere near as frequently, okay? As you can clearly see. And then if you integrate the velocities with respect to time, you get the ground displacements. The movements in terms of displacements is downright ponderous. It's a far cry from the acceleration plot. Here they're going back and forth, but you know it takes its own time doing that. So although this is one specific example, most of the things I said are pretty typical of earthquake ground motion. The frequency, the acceleration plot shows very high frequency typically. When you integrate the accelerations into velocities, the frequency drops. And when you integrate the velocities into displacements, then they are not, the movements of the ground are not frequent at all. They still go back and forth, but uh, relatively slowly compared to the accelerations. The earthquake ground motion characteristics that have the greatest importance for buildings are the duration, the amplitude. Amplitude would be from here to there, how tall those things are. So we have high amplitude accelerations here, for instance. Uh, the amplitude of displacement here is pretty high. Uh, so uh, the uh, the earthquake ground motion characteristics that have the greatest importance for buildings are the duration, the amplitude in terms of displacement, velocity, or acceleration, and the frequency of the ground motion. Now, some basic things. Frequency is defined as the number of complete cycles of vibration made by the wave per second. So complete cycle of vibration, complete cycle would be from zero crossing to this zero crossing, or from this crest to that crest. Okay, you go from an extreme position in one direction, cross the zero axis, go to extreme position in the other direction, cross the zero axis again, and get back to an extreme position in the first direction. Okay, so that would be one wave, and the length of that wave would be wavelength. Frequency is how many of those waves you make in 1 second. So a complete cycle of vibration is from one crest of the wave to the next. Frequency is often measured in units called hertz. Two full waves, if two full waves pass in 1 second, the frequency would be 2 second to the power minus 1, right? 2 per second means 2 second to the power minus 1. And as I mentioned yesterday in our wind discussion, second to the power minus 1 is hertz. So the frequency is 2 hertz. If two full waves pass in 1 second, the frequency is 2 hertz. Now, ground motion at a site. Surface ground motion at a site is actually a complex superposition of different vibration frequencies. It is never one frequency if it is earthquake ground motion. At any given site, some frequencies usually predominate. That is very true. Okay, there are multiple frequencies, but a couple of them would predominate. The distribution of frequencies in a ground motion is referred to as its frequency content. The response of a building to ground motion is as complex as the ground motion itself, yet typically quite different. This needs to be appreciated. Both are complex, but the responses are different, how the ground responds and how the structure responds. Building also begins to vibrate in a complex manner, and because it is now a vibratory system, it also possesses a frequency content. So ground motion comes, hits your building, it sets the building in motion, and because it's a vibratory system, it also possesses a frequency content. The building motion will also have a frequency content. However, the building's vibrations tend to center around one particular frequency that is known as its natural frequency. This is pretty characteristic of building vibration. Okay? The vibrations tend to center around one particular frequency that is known at its natural frequency. Okay, we kind of leave it there for a second, and then another way to think of building response is in terms of natural period. So we discussed it yesterday. Period is the reciprocal of frequency, 1 over frequency. Period is simply the inverse of frequency. Whereas the frequency is the number of times per second that a building will vibrate back and forth, the period is the time it takes for the building to make one complete vibration cycle. So very importantly, F, the frequency, in wind it was called N, remember, but we used F. Most engineers would use F. So F is equal to 1 over the period T. The period, very importantly, period of a structure is proportional to the square root of the mass. So heavier structures would have longer periods, and inversely proportional to square root of stiffness. So stiffer structures would have shorter periods. Okay. So this is very important. Period is proportional to the square root of mass. So heavier structures would have longer periods, and period is inversely proportional to stiffness, which would mean that stiffer structures would have shorter periods. Okay. So generally, the shorter a building is, the shorter its period and the higher its natural frequency. The shorter the period. That's how I think. The shorter a building is, the shorter its period. Oh, okay, it says that. Okay. So the shorter a building is, the shorter its period, and shorter period means higher natural frequency. The taller a building is, the longer its period, and that means shorter natural frequency, lower natural frequency. Okay. On this picture, on this slide, beautiful pictures put together by FEMA that I have just copied. It's absolutely wonderful, trying to explain very basic things. So this is a building, obviously, and somehow somebody has tied a rope to the roof and are pulling on that rope with this tractor. So if the pull is strong enough, the building would move. And then if you, once the building starts moving, if you cut the rope, the building will go back and forth a few times, each time with a shorter amplitude. If the first time it goes 2 inches to the left, the next time it will probably go only 1.5 inches to the left. Okay? So it will go a few times back and forth, but each time with a lesser amplitude, and eventually it will come back to rest. Okay, I think you all would agree that this is what is going to happen. if a tractor actually pulls on a building with a rope tied to the roof, and then the rope is cut, the building will go back and forth a few times, each time with a lower amplitude, and eventually come back to rest. Now, what brings a body set in vibration back to rest is damping. That's another very significant concept that we need to all understand. Okay. So when we swing a pendulum, it starts going back and forth. Newton's law tells us that this motion back and forth will go on forever, but we all know that it does not. Pendulum eventually comes back to rest. It does the same thing as the building. The back and forth motion, the amplitude decreases with every move, and eventually it comes back to rest. In the case of the pendulum, the damping is produced by friction with the air. In a building, damping is produced by the damage that is sustained in the process of going through an earthquake. Okay. So there is something called, now if the damping is at a threshold level or beyond, the threshold level is called critical damping. If the damping in a structure is equal to critical damping or more, then you set the building in vibration. It will come back to rest without vibrating about the position of rest. Critical damping is the least amount of damping that will allow a body set in vibration come back to rest without oscillating about the position of rest. If damping is less than critical damping, then what I described earlier is what is going to happen. The body set in vibration will oscillate a few times, each time with lower amplitude until it comes back to rest. Okay. So damping brings a body set to vibration back to rest. Critical damping will bring a body set in vibration back to rest without oscillating about the position of rest. Now, the very important concept of resonance. When the frequency contents of the ground motion are centered around the building's natural frequency, the building and the ground motion are in resonance. When the frequency contents of the ground motion are centered around the building's natural frequency, a resonance tends to increase or amplify building response. This is why we are kind of concerned about it. Because of this, buildings suffer the greatest damage from ground motion at a frequency close or equal to their natural frequencies. Okay, this is something we absolutely must understand. Okay, I have a short video clip that I would like to play. Dr. Krishnan was at that time a professor at Caltech when this video clip was taken. I think he is now in what was Madras is now Chennai in India. I believe that's where he is. Anyway. Now, what are the implications of these long period waves to our built environment, right? So here is a toy model.
consisting of, think of this toy model as your house, think of this as a, say, 5 to 8 story building, think of this as your 20-story building, and think of this as your 50-story building. Right, so I'm going to excite this model, this toy model, with high frequency motions, and you will see that the high frequency motion will selectively excite this low rise, this house, if you like, much more than this tall building. Right, so that's the high frequency motion. So here's the high frequency motion now. Notice how the low rise structure has gotten tremendously excited by this high frequency motion, which is the motion, the ground going back and forth several times very quickly. Whereas the tall buildings, they're kind of waving a little bit, but they're more or less steady at this point. Right. So now I'm going to excite this toy model by what I would call long period motion that goes back and forth like this that you saw here. That would be the kind of motion that you would see in a deep sedimentary deposit in a big earthquake, in the event of a big earthquake. So here is long period motion now on the same toy model. So here's long period motion. Notice how the little house is just sitting where it is, whereas the tall buildings or these long period structures are going back and forth, getting a lot of response. Right? So the long period motion does not do anything to the low rise structure. It selectively excites our tall buildings. This is the difference between long period motions that you can see in a big earthquake versus high frequency motions. Now, what are the implications?
I thought he did an excellent job explaining this phenomenon of resonance. So I did want to play it for you. Next, you see the record of ground accelerations from one downtown Mexico City location after the 1985 earthquake, the big earthquake there. I had told you previously that one thing you can say about earthquake ground motion is that it is erratic. This ground motion record does not show erratic ground motion. This has very regular pattern to it. There's a very regular period, almost 2 seconds. And so this looks more like the response of a single degree of freedom system to typical earthquake ground motion. It looks like that because that's exactly what it is. Much of downtown Mexico City is founded on an old Aztec lake bed, which means very soft soils. So in this earthquake, the epicenter was a long distance away. I think it was about 180 miles or so away out in the Pacific to the west of Mexico City. The ground motion that arrived on rock to the west of Mexico City was about 4-5% of gravity at most. That would not have caused any damage whatsoever. But the soft soil of the lake bed amplified the 4 or 5% of G on rock up to about 20% of gravity. And that caused devastation to downtown Mexico City structures. It was just awful to see what had happened. Okay, so this was the ground motion that the structures experienced. This is a velocity response spectrum, not acceleration, from that ground motion that shows you a distinct peak at 2.0 seconds. That means the predominant period of that ground motion is 2 seconds. Okay, this is to be compared with the velocity response spectrum of the 1940 El Centro earthquake It doesn't have a distinct peak like this. If there is a peak, it is here at a period of 1 second, okay, just for comparison. Now, this predominant period of 2 seconds of the ground motion means that structures with a period, natural period around 2 seconds would be the most vulnerable to damage in this earthquake. However, here you have to be a little knowledgeable. Structures, particularly concrete masonry, the period lengthens as the structure goes through an earthquake and damage accumulates. The structure softens up, the period lengthens. Okay, so you may start with a period of put 1.5 second, and as the structure goes through the earthquake, the period may lengthen into 2 seconds, and then it is in big trouble because that is the predominant period of the ground motion. So you would expect medium rise buildings period of, let us say, 1.5 to 2 seconds to be the most affected. Now that's exactly what we observed. This is the Ministry of Transportation, Telecommunication and Transportation, downtown Mexico City. It had a this L shape that didn't help, but mostly it was in the long height range. So this building, it's not totally destroyed, as you can see, but the damage was terrible, and because of that, Mexico lost telephone connections with the rest of the world for, I don't remember, it was hours, if not days. Yeah. So by contrast, these colonial buildings are probably, how should I say, the construction may or not have been ideal. Anyway, because of their short height, nothing happened to these buildings except for some flaking of plaster. That's about all the damage that you could see. And at the other range of the spectrum, this Latin American tower, 40 stories tall, so 4 second or so period. This was out of the range of the earthquake. Predominant period, remember, was 2 seconds. So short buildings were not affected, tall buildings were not affected, but the mid-rise buildings paid a huge price. Now, another aspect of the same thing, I don't know, another aspect, another look maybe at what we are talking about. So the top caption is saying, buildings in a city lie on different soils. That is true. Now, what is plotted down here is the structural damage intensity versus depth of soil. Now, what damage intensity is kind of immaterial. Let us think in terms of damage potential, maybe. I don't know. Anyway, so depth of soil, when it is rock, it is short period ground motion. As the soil deposit gets deeper, the period of the ground motion will be longer and longer, as you saw in Mexico City, 2 second period, because it was very soft soil, overlying rock, and it was deep deposit of soft soil. So for very shallow soil deposits, shallow thicknesses of soil overlying rock, the ground motion was short period ground motion. The 3 to 5 story buildings were the most excited, but for the deeper soil deposits, when we were dealing with long period ground motion, it is the taller buildings that were more excited. So for deeper soil deposits, the taller buildings would appear to be more vulnerable to earthquakes. For very shallow soil deposits over rock or on rock itself, the shorter buildings would be the ones more vulnerable to earthquakes. Now, acceleration has important influence on damage because as an object in motion, the building obeys Newton's. Anyway, so this is saying the no, maybe I should read it the way it is. Yeah, so acceleration has important influence on damage because as an object in motion, the building obeys Newton's second law of motion. The simplest form of the equation which expresses this law is force equal to mass times displacement, mass times acceleration. So acceleration has important influence on damage because force is equal to mass times acceleration. Where there is acceleration, you are inducing force. So inertia force, the force acting on the building is equal to the mass of the building times the acceleration. The force acting on the building is equal to the mass of the building times the acceleration. So as the acceleration of the ground and in turn of the building increases, if the acceleration of the ground increases, the acceleration of the building will also increase. And as that increases, so does the force which affects the building and the potential for damage to the building. It is important to note that inertia force F is actually what is known as the force F is actually known as the inertia force. That is, the force is created by the building's tendency to remain at rest and in its original position, even though the ground underneath is moving. Okay, this I think is a good point to take our break. Okay, so this is a yeah. I'll take you from there. Let me see, 27. So we'll come back at 32 minutes after the hour. Okay, thank you.
Good, Dr. Ghosh.
Thanks. Okay, I think it's time, so we will start again. So I will read this and then go from here. It is important to note that F is actually what is known as an inertia force. That is, the force is created by the building's tendency to remain at rest and in its original position, even though the ground underneath it is moving. So that is shown through a picture on the next slide. So because of earthquake, there is acceleration of the ground and the foundation has started moving. The movement is every which way, but here we are showing the left to right movement. The foundation has moved, but the mass which is at the roof level wants to stay back where it is. It doesn't want to go with the foundation. Okay. So ultimately, what we end up with is something like shown in the picture. So the foundation moves that far, the roof moves only a part of that distance. It is the reason that the mass doesn't follow the movement of the foundation is that there is essentially a force acting in the opposite direction to the movement. Okay. So this is moving. The reason that this is not moving together with the foundation is that there is a force that is keeping it from moving as far as the foundation. And this is called the inertia force. The important thing, that the important point for you to note is that the inertia force is in a direction opposite to that of the earthquake ground motion. Okay? So earthquake ground motion causes the inertia force, but the direction of the force is opposite to that of the ground motion. So when we have, let us say, one-story frame or whatever structure, okay, subject to earthquake ground accelerations, that's what, so U sub G is displacement of the ground, U sub G dot is the first derivative of that velocity of the ground, U sub G double dot is the double derivative, the second derivative of the ground displacement, and that is ground acceleration. Okay. The ground acceleration is a function of time. So this system, the building subject to ground acceleration, is equivalent for our purposes of analysis to a fixed base structure where the base doesn't move, but the mass is subject to a force, an inertia force equal to minus m times U sub G double dot T. Okay, so an inertia force equal to mass times the ground acceleration and in a direction opposite to the ground acceleration is equivalent to a structure with ground acceleration applied to it. So in some circumstances, dynamic amplification due to near resonance can increase the building acceleration to a value 2 or more times that of the ground acceleration at the base. So here we are taking the acceleration here equal to the acceleration at the base. That may not be the case. This value may be higher, but that's almost incidental. So in some circumstances, dynamic amplification can increase the building acceleration to a value 2 or more times that of the ground acceleration at the base. Generally, Buildings with higher natural frequencies or short periods tend to suffer. The last two paragraphs are very important. Short period buildings suffer higher accelerations but smaller displacements. Higher accelerations but shorter displacements. Okay, so if you are thinking of damage to partitions and things like that, that is less likely to happen in a rigid building, in a short period building. But the high acceleration can do things to uh, uh, anything supported on the floors. The floors will undergo large accelerations. So if you are supporting, doesn't have to be machinery, anything on the floor, you will need to watch it. The supports will be subject to high accelerations. Okay? The longer period buildings are the other way around. They suffer more displacements but less acceleration. So more displacement may cause damage to non-structural elements and things, but the lower acceleration is a benefit when it comes to elements that you are supporting. Now, the concept of load path. This is also obviously very fundamental and very important. So we have a building of some kind, could be multi-story, could be one level, doesn't make any difference. This is the roof diaphragm, as we call it. This is a slab on the roof which, under lateral loads due to wind or earthquakes, bends in its own plane like a deep beam. So when it bends under lateral loads like this, there is compression along this edge, tension along that edge, and shear along edges parallel to the loads. Now, those loads could be seismic forces, okay? And we will see how we go from the essentially the ground accelerations to seismic forces at the various floor levels. That we will do, I don't remember, either Monday or Tuesday. Okay? But in design, seismic forces become as shown in this picture. And when the seismic forces act on the diaphragm is subject to compression, tension, and shears. Okay? Those shear forces are transferred to the frames and shear walls supporting the diaphragms. The frames and shear walls bring those forces down to the footings, which then transfer them down to the ground. Okay, so the load path in this case consists of the diaphragm, the vertical elements of the seismic force resisting system, the frames, shear walls, whatever they have, the foundation or the footing, and obviously then at the end, the ground underlying the foundation. Okay, so so when we talk about load path, it is how the load goes from point of application down to the ground via which structural elements. So load paths from point of load application or origin down to soil underlying foundation. Preferably, our load paths should be direct. That is more important than you think. Load path should not be convoluted. The more direct the load path, the better off you are in seismic situations. And also very, very preferably multiple load paths. Something happens to your primary load path, something will have to take its place. Okay, multiple load paths. That is the concept of redundancy. So the load path should be as direct as possible, and we preferably should always have multiple load paths. Okay, earthquake damage mechanisms. The ground shaking itself can cause damage. And so far we have been talking only about ground shaking, but there are various modes of ground failure as well. Rupture of the ground, liquefaction, landslides, lateral spread, and also tsunami and size, which are caused by earthquakes. Okay, so let us look at examples of these things, and then we will go on to topics that are still very important. So seismically induced ground motions, we know this by now. Seismically induced ground motions produce inertia forces in structure, and they can cause complete collapse of a structure, partial collapse, building interaction, basically hammering, or interior damage, damage to the non-structural elements, as we call them. Yeah. Here I have some old pictures that I don't know, it probably will never happen, but I have pictures all over the place, but to collect them and it is a huge project. Anyhow, so this is Agadir, Morocco, 1960, a hotel that you can obviously see has completely collapsed in the 1960 Morocco earthquake. This is a famous picture, 1971 San Fernando earthquake in the Los Angeles area, the hills north of Los Angeles. This was a hospital not very far from the epicenter, Olive View Memorial Hospital. At the time the earthquake hit, the hospital was relatively new, and it underwent what is being described here as partial collapse. And you can see this is not a redeemable situation when something that like that happens to your column. And the reason was, it was a soft story. The column supported shear walls above. Anyway, whatever the reason, we had partial collapse of this important hospital. And when hospitals don't function after an earthquake, the community is in significant trouble. Hammering. Buildings. This is this may have been my picture. I don't remember. This is, I believe, this was the Supreme Court of Mexico after the 85 earthquake, and so the two buildings very close together of different heights, and hammering becomes a problem when the floors of the neighboring buildings are not aligned. When the heavy floor of this building goes and hits against the mid height of the column of the neighboring building, it doesn't take much for the columns to fail and the building or portion of building to come down. And that's precisely what has happened in this case. Okay, hammering can have sometimes not much consequence if the floors are aligned. Floor of one building hits against the floors of neighboring buildings, then it should be a manageable situation. But if the floors of a building, heavy floors, hit against the mid heights of columns of neighboring buildings, mid height or wherever along the length of the column, then partial failure is not at all uncommon. So buildings spaced too close together can hammer together and cause severe damage. I have seen way too many of these. And then non-structural element damage. The false ceiling has come off, lighting fixtures. This is all the time. Every earthquake you will see. The building may look fine from the outside, but you go inside and you will see a lot of damage. This is very typical. Okay, ground failure can be fault rupture, liquefaction, landslide, lateral spread. This is an old picture, 1906 San Francisco earthquake. You see the fault rupture here that has displaced the fence. And in Turkey, after the 99 earthquake, I would not remember the name of the place. This was away from Istanbul in a rural. Anyway, I have with my own eyes seen fault rupture go through somebody's bedroom. So part of the house was here, including partial bedroom, and the remainder of the house with the remainder of the bedroom was some distance away because of fault rupture. These things actually have happened. No question. The liquefaction, soil or ground becomes like liquid. Your house, this is, I'm exaggerating, but it essentially becomes like a boat. It's not founded on soil anymore. It's supported by liquid, and then piles that depend on friction with the soil just pull out. This happened in a big way in Niigata, Japan, 1964. I have seen a number of instances of this after the Bhuj earthquake in India. That was 2001, something like that, 2003. I don't remember the exact date. So number of occasions I did see exactly that, piles pulling out because of liquefaction. Lateral spread looks, I think the picture is pretty descriptive. This is failure of the soil. We saw huge amount of that after the Chile earthquake, 2011, when we went down to the epicentral area near Concepcion. There was a whole lot of this lateral spread that you could see. Landslides, I think you are all familiar with. Here is a pretty big instance of that. This is in the same earthquake. This is Alaska earthquake. Olympia, Washington is so down after Alaska, south of Alaska. This is Canadian territory for quite a while, and then comes the state of Washington. So this is quite a ways from, but even then, landslide, and these were railway lines on level ground, and obviously you see what has happened. Tsunami, I think we are hearing quite a bit these days after the Tohoku earthquake caused tsunamis in 2011. Seismically induced sea waves, that's what tsunamis are. Seismically induced fluid motion in reservoir or lake, not like inland bodies of water, not the sea, are called seish, and both can have pretty devastating effect, although tsunamis are typically much stronger. So in the 2011 Tohoku earthquake, I have so many pictures. This was just absolutely awful. Anyway, this is a seaside community before tsunamis came or the earthquake came, and you see what has happened to it after the earthquake. Total, complete devastation. Okay, so these phenomena are to be taken seriously, but sometimes there is nothing we can do. Ground shaking, the effect is wide, not localized, but we can do something about it. We can design our buildings to resist ground shaking, or at least to perform satisfactorily for us in ground shaking. Fault rupture has local impact, and nothing we can do about it if it happens. So what we can do is not to build where we know that there are known faults and there are restrictions in the IBC that you cannot do that. Landslides also are local in their impact, and they are not containable. There is nothing we can do to to uh, to protect our building from effects of landslide. Okay? So it is better if we can avoid them. That's the best. Don't build on a site near where you can have landslide. So liquefaction is better to avoid, but that is something we can do a few things about. We can try to improve the soils at the site. There are ways of doing that. Tsunami these days, there is tsunami resistant design starting with AC 716 that is pretty sophisticated, and we have every reason to believe that that will work. And SAISH is the same thing. You will do similar things, maybe not the same. Okay. So avoid if you can, but the tsunami, I don't know, can be avoided because it affects large areas. You cannot just, so if avoid, yeah. Anyway, tsunami resistant design is now becoming, and will soon become, I would say, significantly more common. Okay. There was a question yesterday why we don't do special detailing in wind design, and I said that our structures are designed to remain elastic under the design wind forces, but we deliberately design for inelastic behavior of our structures in the design earthquake. Okay. So we'll start getting into that right now. Okay. So what we are looking at is the the load displacement relationship of a particular structure subjected to a particular earthquake. One structure in one earthquake. The forces induced in the structure as it goes through the earthquake are plotted on the y-axis, and the displacement suffered by the structure in the process of going through the earthquake are plotted on the x-axis. Okay, so the lateral force on the y-axis, the lateral displacement on the x-axis. Initially, we are showing elastic response of this particular structure to this particular earthquake. Elastic does not have to mean force proportional to displacement as shown in the picture. There is nonlinear elasticity, which is fine. Elastic really means no residual displacement. The earthquake passes, we get our structure back intact, no damage to be repaired. And very importantly, we get our structure back located where it was before the earthquake, not some distance away, as tends to happen. Okay, so the elastically responding structure develops a force equal to F sub u in this particular earthquake and suffers a total displacement equal to delta sub u. Now, if I were to turn around and tell you that we are required to design this particular structure to respond elastically to this particular earthquake, the immediate conclusion would be that we must build a strength into our structure equal to F sub u, the maximum force that had been induced in the structure by the earthquake. We must have strength at least equal to F sub u for the structure to behave elastically in this earthquake. If we decide we cannot afford that high strength, that all we can afford is a much lower strength, F sub E, then what would happen if the same earthquake would come hit our structure is that as the earthquake-induced force equals and then exceeds the supplied strength level F sub E, the structure will start cracking and yielding in places. That will be the beginning of inelastic displacements, which will not follow the flat top that I have in this idealized picture. But the fact remains that at that point, we will no longer have our displacements recoverable. There will be damage associated with further displacements. The structure will have to be repaired. Okay. So the difference between the stronger structure with the higher strength level and the weaker structure with the lower strength level is that the entire displacement suffered by the stronger structure is elastic. It is all recoverable. There is no damage associated with it. But much of the displacement suffered by the weaker structure is inelastic. It has damage associated with it. Okay. Now, many observations and also a lot of analytical work has shown us that the total displacement suffered by the structure, total displacement delta sub u, is about the same, not precisely the same as shown in this idealized picture, but about the same whether structural response is elastic or inelastic to various degrees. Okay, so the total displacement suffered by the elastic structure and the total displacement suffered by the inelastic structure are about the same. The big difference, obviously, is that much of the total displacement in the second case is inelastic. Now, this inelastic displacement has to be limited to values where they do not cause collapse of the structure. That's the first thing. Okay, so we will allow inelastic displacements, but not to the extent that the inelastic displacements will cause collapse of our structure. That would be that would compromise life safety. Okay, so the way we say it is that the inelastic deformations will have to be within the inelastic deformation capacity of the structure. Inelastic deformation capacity is the inelastic displacement that the structure, the inelastic displacement over which the structure can sustain full factor gravity loads. So inelastic deformation capacity is the inelastic displacement over which the structure can continue to carry full factored gravity loads. That automatically means that there is no collapse. The higher the deformation capacity, the longer the range of inelastic deformations over which gravity can be sustained. The lower the inelastic deformation capacity, the lower the inelastic deformation range over which gravity loads can be sustained. Okay. So the higher the design strength level, the lower the need for inelastic deformability, and the lower the design strength level, the higher the need for inelastic deformability. Inelastic deformability comes from proper detailing of the members and joints. Okay? So if we want to design for low strength levels, we will have to be prepared to do pretty fancy detailing of our members and joints in order to have high inelastic deformation capacity. If, on the other hand, we are content to design for a relatively high design force level, then we will not need all that terribly much inelastic deformation capacity. Then our detailing may be, relatively speaking, crude, not that fancy. Okay, so these are the very basics. In our building codes, the R factor, the response modification factor, sets the design force level. When R value is high, we are designing for a very low design force level. When R value is low, we are designing for a high design force level. So a low R value does not require fancy detailing, but a high R value, which translates into low design force level, requires fancy detailing. Okay, so in our codes, there are three recognized levels of detailing: ordinary, intermediate, special. Special is what I was calling fancy detailing. Ordinary is what you will do where there is no seismic risk, no appreciable seismic risk. Intermediate is something in between. Okay? So ordinary, intermediate, special. Theoretically, we should be allowed to design for, we should be allowed to design any structure anywhere for a low design force level if we are prepared to do the fancy detailing that goes under the title of special detailing. In other words, at least theoretically, seismic design is an exercise in trade-off between strength and inelastic deformation capacity. The higher the strength, the lower the need for inelastic deformation capacity. The lower the strength, the higher the need for inelastic deformation capacity. In reality, our codes do not allow us an unrestricted trade-off between strength and inelastic deformability. Okay? We will discuss seismic design categories in the coming days. For now, seismic design category A is essentially non-seismic. There is hardly any seismic risk. B is low seismic risk, let us say. C is moderate, and D, E, and F are high. So a structure assigned to seismic design category A does not require any seismic design, period. A structure assigned to design category B requires only ordinary detailing. However, here we will allow the higher levels of detailing if the engineers wants to do them, and he can benefit from the higher R values and lower strength levels. So if you have a design category B structure, you can still choose to use special moment frames benefit from an R value as high as 8, which will give you very low design force levels. But that, I can tell you, is never cost effective. The fancy detailing costs a lot of money. You are much better off providing higher strength and a lower level of detailing. If your design category is C, you have to, as a minimum, do intermediate detailing. Ordinary detailing is not an option that is allowed you anymore. The code doesn't allow that. Okay, you cannot do ordinary detailing for a design category C structure and take the penalty of a lower R value. That is not allowed. The minimum you have to do is now intermediate detailing. You are allowed to do special detailing and take advantage of a higher R value. That is allowed. If your structure is assigned to design category D, E, or F, Bangladesh, you don't have E or F. If you have design category D, you shall, as a minimum, do special detailing. You have no choice in the matter. You are not allowed to do ordinary detailing or intermediate detailing. Okay, so those are very basic things that you absolutely must understand and remember. Okay, pretty much the final thing today. I don't believe I put anything after this. I don't know. I may be surprised. We will see. Okay, the earthquake force resisting structural system. Okay, there are 4 basic systems: the moment resisting frame system, the bearing wall system, the dual system, and the building frame system. I will spend time on this. Please follow me very closely. Please try to fully understand and retain what I'm saying, because this stuff is vitally important. And I see all the time that these are not always fully understood. Okay, so moment resisting frame system, beam column frames or slab column frames, as the case may be, resist 100% of the gravity loads and 100% of the lateral loads. 100% of the gravity and 100% of the seismic forces, with no shear walls doing anything for you. The term shear wall, I would like to explain. A shear wall, like any wall, carries gravity loads, but in addition, it resists or carries in-plane lateral loads, in-plane as opposed to out of plane. Okay, whenever we use the term shear wall, we are talking about an element that carries gravity and in-plane lateral loads. Okay, so in a moment resisting frame system, the slab column or the beam column frames carry all the gravity and all the seismic forces with no walls doing anything for us. Okay, now we have ordinary moment frames. So first of all, that's the definition of a moment resisting frame system. You can do it in concrete, you can do it in steel. In masonry, there is no moment resisting frame system. One was tried some time ago, was put into the code, but there were no takers. Nobody was building them. That has been deleted. And in wood, you don't do moment resisting frames. So concrete or steel. And in both materials, we have ordinary moment frames, intermediate moment frames, special moment frames. So my point is that you have to take the structural system and then the material of construction and then the level of detailing, and then you have one of the entries in the table that you have in BNBC that lists the structural systems. It is table 12.2-1 in ASCE 7. Okay? So you will see ordinary moment frame of concrete. That would be the system. So moment resisting frame system. Bearing wall system is where shear walls carry all the gravity, and the same shear walls that carry all the gravity also resist 100% of the seismic forces. I want you to understand this. Okay, the same walls are doing both, carrying gravity and resisting earthquake forces. This is why this system has the lowest, some of the lowest R values, because there is no redundancy. Something happens to these walls in an earthquake, there is no gravity carrying system anymore. Okay, so that is a bearing wall system. Then there are combination frame shear wall systems, which can be designed in two ways, as building frame system or dual system. In a building frame system, the shear walls are designed to resist 100% of the design seismic forces, and the frames carry all the gravity. So there is total separation between the gravity system and the seismic force resisting system. Seismic forces are resisted by the shear walls, the gravity resisted by the frames, and the how do I want to say it? The thing to watch out for when you do one of these systems is that there is the very important deformation compatibility requirement. The frames must continue to carry full factored gravity loads as they deform together with the seismic force resisting system consisting of shear walls all the way up to the design earthquake intensity. Okay, this has to be checked and satisfied. Okay, so the frames carry all the gravity, the shear walls carry all the lateral, all the seismic forces, and deformation compatibility is maintained between the two systems, meaning that the frames must continue to carry full factored gravity loads all the way up to the design earthquake deformations of the seismic force resisting system. Okay, in code language we say the two things I think are kind of important. The frames must carry substantially all the gravity is what we say in our codes. Doesn't have to be 100.00% of the gravity. Okay, the weights of the shear walls do not have to be carried by the frames. So the frames must carry substantially all the gravity, and they must be substantially complete or essentially complete. Essentially complete frames must carry substantially all the gravity. Again, essentially complete frames may mean that the frame is not 100% complete, but so there is a little bit of leeway that the code gives you, but basically 100% of the lateral forces go to the shear walls and the frames carry all the gravity. Dual system is where Both the shear walls and the frames participate in resisting gravity as well as lateral loads. Frames carry their share of gravity and lateral loads. Shear walls carry their share of gravity and lateral loads. You need to do an interactive analysis of the frame shear wall system. That analysis will show you that near the bottom of the structure, almost the entire story shear goes to the shear walls, almost nothing to the frames. But as you move up the building, the frames pick up more and more with the shear walls unloading on the frames. You have to design the frames and the shear walls on that basis. You cannot decide as an engineer that for your dual system building, you will design the shear walls for 60% of the lateral loads and the frames for 40%. That is not your decision. The structure gets to decide. You have to do an interactive analysis that will show that the distribution in the first story is 95% going to the shear wall, 5% going to the frame. But in the 30th story, it is the other way around, 95% going to the frames and 5% to the shear walls. You have to design on that basis. Okay. And that then leads to the second condition. If you design just on the basis of interactive analysis, then you will end up with very flimsy columns at the bottom of your structure because at the lower levels, the frames don't carry any lateral loads. So the second requirement of a dual system is that the frames, independently of the shear walls, must be designed to resist at least 1/4 of the design lateral forces. Okay, the frames independently of the shear walls must be designed to resist 1/4 of the design lateral forces. So this is the so-called backup frame concept that has been with us since San Fernando. If something should happen to the shear walls, the frame should still be standing up carrying gravity loads for us. Okay, so the dual system, the frames and the shear walls must be designed to carry their share of gravity loads and lateral loads. And in addition, the frames must be designed to resist at least 1/4 of the design lateral forces. Those force systems are defined systems. Then we build a whole lot else that is not defined in the code. Those fall under the umbrella of undefined structural systems, which basically have to be designed by comparison with one of the defined systems. That's pretty much what we say in the codes and standards. Okay, so as far as concrete systems in AC7 and BNBC, this is what we have. Moment frames. We have ordinary moment frames that can be cast in place or precast. We have intermediate moment frames which are cast in place only. There is no intermediate precast moment frames in AC7 or BNBC 2020. You don't have a lot of precast anyway. And then special moment frames which can also be cast in place or precast. Shear walls, we have ordinary shear walls which can be cast in place or precast. Ordinary shear walls can be used in design category C. There is no intermediate shear wall that is cast in place. There is an intermediate precast shear wall that you would use in design category C. No cast in place intermediate shear wall, but we have precast intermediate shear wall. No precast intermediate moment frame, but we have cast in place intermediate moment frame. And then special shear walls can be cast in place or precast. So this is pretty much the inventory of concrete systems that we have in our codes and standards. Okay, then I knowing that I didn't pack today with a whole lot of slides, I would like to play this clip, which I think this is I don't remember if it. I remember getting into the building. So it was large scale. Whether it was full scale, I do not remember. This is on the not on the campus. University of California, San Diego has an outdoor shake table facility. And this test was done there on the outdoor shake table of the University of California, San Diego, a multi-story building that was large scale, and it was a real building. It had everything that a building has: a staircase, functioning elevators, water tanks, and things like that on the roof. One floor was equipped as a hospital surgical floor, another was a hospital patient floor where patients lay in bed, did not undergo procedures. There was one was an office floor, one was, I believe, a school floor, like classroom. And the fifth level, I don't remember now. Anyway, the idea was to study the performance of the non-structural systems in the building. This was a very ambitious test, very well done, and it's a multi-volume report posted on UC San Diego website. Tara Hutchinson was the one that Tara was the principal investigator. All the reports have her name. So if you search under Tara Hutchinson, UC San Diego, you will find these reports. Anyway, the clip is from that test, and I think it tells you quite a bit about earthquake ground motion and what happens to buildings in it.
It's time for the ultimate test, maximum considered earthquake ground motion. This is an earthquake with a 2,500-year recurrence interval. Codes and designs for this motion have the performance expectation that the building will not collapse, but will lose functions and be severely damaged beyond repair. 9, 8, 7, 6, 5, 4, 3. The violence and severity of the quake is clear. This would be a frightening experience not soon forgotten. Forces and displacements on the structure are extreme. At points during the shaking, floors 2 and 3 are displaced by nearly a foot in both directions. The heavy upper cladding is shaken violently, but remains attached. The lower cladding tears like paper. Interior furnishings are thrown about by the violent acceleration. Those that are unrestrained are tossed about like so many toys, while anchored items ride out the seismic storm, jerked to and fro along the walls and floors to which they are attached. Close inspection reveals that the building suffers irreparable damage.
I think this building in a real world situation would be condemned. The columns, base of the columns, the concrete is falling off, especially the two columns on the east. There is a beam at the top of the first story where there is a full plastic hinge formation with a lot of concrete that detached. You see these blocks of concrete here. We can see the rebars. They are naked now. At different floors, you can see the formation of the punching failure mechanism of the slab around the column, not far from really collapsing. From the third floor to the fourth floor, the stairs are detached. They are hanging. There are a lot of gypsum board, huge gypsum board that detached, that fell off. At every floor, frame of the elevator door has been seriously damaged. The doors are locked, in an oblique fashion.
But the building has done its duty. It bent and cracked, but did not collapse.
It satisfied the design objective. The structural system should still stand, even though maybe close to collapse, but still stand.
Okay. With that, I'm open to questions.
Thank you, Dr. Ghosh. Thank you for this wonderful presentation. Personally, I have attended this presentation on twice or thrice, but every time I appreciate it a lot, and hopefully everyone who is present today is appreciating this webinar that you have done. It goes over the basics, and you cover a lot of things in a very simplistic manner. So thank you for doing that. So I will start with the questions. Dr. Ghosh, are you there?
Yeah.
Okay.
You haven't said anything yet, right?
No, I did. I was saying that this presentation was really good.
Oh, no. That I heard, but no
Yeah,
questions so far.
No
Yeah.
questions yet. No.
Yeah.
No, I'm just going over one
Yeah.
by one.
Yeah, sure.
So we designed the building as per code with zone coefficient. Most of the homeowners want to know during the building design or while construction, that what magnitude of an earthquake could be registered by the building. What should be the exact answer, these homeowners?
There is no exact answer. As I explained to you, magnitude doesn't mean anything until it is tied to some source. So you can you can tell them that this is good for a magnitude 7 earthquake on the Tauki fault or something like that, but without that addition, magnitude 7 earthquake or whatever does not make any sense whatsoever. So there has to be, for somebody to ask what magnitude earthquake is this building good for simply shows ignorance on his part. You need to educate him, give him the basics of what magnitude means, and then you can volunteer that if something were to happen on the Tauki fault, we are good for, or whatever it is. That is a number that can be figured out, not easily, but can be done. But just good for magnitude such and such without any further elaboration, that doesn't make any sense. And the zone doesn't tell you that. Like there is no correlation between zone and what magnitude earthquake and what fault. There is very indirect. It gets very complex, but anyway, the answer is what I gave you first.
Okay. Is there any restriction to increase the time period up to 40% during earthquake calculation by equivalent static method?
I haven't. You would increase period 40% because you are using static method. Is that what the question is?
Yeah.
I don't know any such thing. I don't know. No. I don't know.
Yeah.
I don't think so. It's not making a lot of sense to me. Maybe there is something, but the question probably doesn't reflect, the actual inquiry may not have been expressed properly. I don't know.
Okay. So the next question is calculate seismic load, dead load. To calculate seismic dead load, 100% of dead load and 100% of permanent heavy equipment load is considered. However, for live load, seismic dead load is 25% to 50% of live load. Can you explain this?
I don't even understand the term seismic dead load, seismic live load. I don't know what you are thinking. Dead load is dead load, live load is live load, seismic forces are seismic forces. There is no such thing as seismic dead load. And what you apply, you design your structure for the specified dead loads, which include superimposed loads. You design your structure for reduced live loads. You design your structure for code prescribed earthquake forces. And this is where the load combinations come in. So you combine the effects of dead loads, live loads, earthquake forces through the design load combinations. So I am not understanding seismic dead load, seismic live load, and whether it should be one half or what. I don't know. You have.
I'm guessing he's asking, like uh, mentioned seismic dead load, but I'm guessing he's asking about that lumped mass that is used. So in that you used 100% of dead load and 50% or 25% of live load. I think so. He's asking that. I don't know exactly.
The only time we have to include a part of the live load in seismic mass is if it is a storage facility. The idea is the so if your question, as both he suspects, is about what we call seismic weight, that is a term in AC7 and BNBC, seismic weight or seismic mass. So that is the dead load of the structure, except in storage occupancies, we include 1/4 of the designed live loads. There may be a little more detail to it in BNBC, I don't remember without checking. The idea of the seismic weight is that is the weight of the structure when the design earthquake hits. So if it is a storage facility, a warehouse, it is extremely unlikely that it will be entirely empty at the time of the earthquake. So we include 1/4 of the designed live loads. So that is the kind of logic. So if that's what you are asking, yes, seismic weight typically includes 1/4 of the designed live loads for storage facilities. BNBC, I think, is a little more complicated. I have to go back there. I haven't looked at it for a while. but it is defined. Seismic weight is a term that is defined. Go look at the definition and you will have your answer.
I think he's asking that only.
Okay.
In Mercalli scale, why in magnitude 10 a masonry building stands and not a framed building?
There is no why. This is how that is just a description of intensity 10 on the Mercalli scale. There is there is no explaining why. That's how magnitude 10 is not magnitude. Intensity 10 is defined on that scale.
Just going through the questions. Should we use the vertical component of earthquake loading during the punching calculation of footing or mat?
If you are doing seismic design, I said, I don't remember which day, the term E, earthquake effect, is made up of two parts. The horizontal earthquake effect and the vertical earthquake effect. Yeah. This is considered in the design load combinations. So the load combination that says 1.2 dead plus 0.5 live plus 0.2 snow plus 1.0 E, in that load combination, E will be taken as rho times E sub H, which is the horizontal component multiplied by the redundancy factor, plus 0.2 S sub ds times D, which would be the 20% of the short period spectral acceleration multiplied by the dead load. Now, when you combine terms, what we will have done is increase the dead load factor from 1.2 to 1.2 plus 0.2 S sub ds. If S sub ds is equal to 1, the dead load factor will now be 1.4 in recognition of vertically downward earthquake ground motion. In the counteractive load combination, 0.9 dead plus 1.0 E, we will have made the load factor 0.9 minus 0.2 S sub ds, which will come to 0.7 when S sub ds is equal to 1. So we will be decreasing the dead load factor in the counteractive load combination in consideration of vertically upward earthquake effect. So this we do for all structural members in seismic design, okay? And seismic design starts with design category B. In foundation design, we will do exactly the same thing. There have been without looking up again, I cannot tell you. There have been, at least in old times, some exemptions from this for foundations, but without looking again at BNBC, I don't want to tell you there are exemptions or there aren't any exemptions. So before I teach that in one of the seismic modules, I will look that up and I will tell you. But in general, that's what we do. How we account for vertical earthquake effect. We increase or decrease our dead load factor. Okay? And that is for all structural members, including foundations, unless there is a specific exemption for foundations, which I will look up.
Okay, Dr. Ghose. Um, if we insert a base isolation mechanism, um, will the response reduction factor change, or will it just change the damping factor?
Read that again.
If we insert a base isolation mechanism between foundation and superstructure,
Hmm.
will the response reduction factor R change, or there will be change in damping factor?
The response modification factor of the superstructure will not change. It will be what it is. What you will be doing is cutting off the ground motion that will be transferred to the structure will be very different. So I would hesitate to call it damping either. It's probably closer to that, but the best way to look at it is that you are cutting off the ground motion. In the absence of the slip that takes place, the motion imparted to the structure would have been much higher than it would be if you have the isolator. So the R factor of the superstructure doesn't change.
And a pile foundation be used in case of soil liquefaction?
I what do I want to say? There is definitely no prohibition if that's what you are asking. Okay. But liquefiable soil would be site class F. In BNBC it is called S1, S2 or something, I forget, the worst. And on that type of soil, your design has to be based on site-specific analysis. So depending upon what you find out about your soil, your pile design may have to be very different. I do not know, how should I say, size specific is something that is very difficult to talk about because you never know what you will find when you do a size specific analysis. But I can tell you that in general, you will be much better off improving the site. And that can be done by injection of what was used to be called soil cement. Now it has a fancier name. I forget now. Anyway, so so improving the site will be your much better bet before inserting the piles or casting the piles, because you have seen in the case of liquefaction, piles do actually pull out. So if you don't want to take that risk, then improving the site will be a much better way to proceed.
Thank you, Dr. Ghosh. There are a lot of questions now, so I'll just read out the relevant questions. In a dual frame system, we design the moment frame itself to carry at least 25% of base shear.
Mhm. Yeah.
What about the same structure for wind design?
There is no dual system in wind design. You have to. this is this is all this is all seismic, and if you want to do a dual system in wind design, you will just do the interactive analysis. No 25%. It doesn't make any sense. The whole basis of the 25% frame If something should happens to the shear walls, the frames will still be standing up. And the basis of that is that the frames have much more inelastic deformation capacity than shear walls do. Okay? In wind design, we are not counting on inelastic deformations anyhow. So wind design is considerably simple that way. Yeah, we don't even call them dual systems. We simply call them shear wall frame interactive systems, and we design them on the basis of interactive analysis. There is no 25% backup frame. That is the short answer to your question. This dual system concept is simply, it doesn't apply unless there is inelasticity in the picture.
Okay, Dr. Ghosh. Avoid soft story problem. Is it permissible? Uh, this is I have to rephrase the question.
Mm.
I'm not understanding this question. I will go to the next question.
Okay.
Yeah, it's the English is weirdly, and I'm not getting what he's asking.
Mm.
There are a lot of questions, like it seems the basics. Like one is asking why we should not go for strength-based design for earthquake force.
Why we shouldn't go for what?
Why we should not go for strength-based design for earthquake force.
We do strength-based design. What
Yeah,
do you do?
I'm not understanding like why
Yeah.
this question was asked. In BNBC, normalized or simplified response spectrum
Mm.
has been developed considering soil category and building type.
Mm.
So is it enough for dynamic analysis? Because we do not know the detail of the next earthquake. Oh, so he's asking in general about response spectrum.
Yeah, response spectrum. Again, in one of the lectures, I will discuss the basis, but the answer is yes. If you are doing modal response spectrum analysis, the spectrum in the code is definitely good enough. Definitely.
And this will be covered in the future
Yeah.
lectures
Yeah.
in
Yeah.
detail.
Yeah.
So don't
Mm.
worry about response spectrum right now.
Yeah.
Um, Again, a lot of questions will be covered in detail in the upcoming webinars.
Yeah, we
So
have seven more lectures to go. We will go in depth
yeah.
into most things.
Is it possible to know how much level of earthquake in Richter scale of a building uh, is it possible to know how much level of an earthquake in Richter scale a building can endure if the building is designed considering modern earthquake resistant design?
Yeah. That is a better question than what magnitude of an earthquake. And Yeah, that should be possible. Just by looking at the scale, I think you can figure that out. It will be in that 8-9 range, I would think.
Can you
Damage,
please cite? Oh, sorry. You
yeah,
explain.
no, I was thinking, I don't remember exactly, but damage to modern buildings is caused by intensity 10, I think. So up to intensity 9 would be intensity 9 would be a good answer, I would think. Yeah, sorry, go ahead.
Yeah. Would you please cite a reference book to design building frame system?
Design of building frame system is in our book, right?
Yeah.
Our concrete book.
Yeah, it has all the frame systems mostly.
Yeah. So we have a publication, Design of Concrete Buildings for Wind and Earthquake Forces. Who publishes? Our company, ICC. I don't know. Anyway, you can get hold of this if you go to the internet, I think.
Yeah. Yeah, that covers most of the building frame systems, and
Yeah,
it is based on AC 705.
yeah,
So
okay,
yeah,
good. Whether it is still available, I don't know.
yeah, that needs to be checked.
Yeah.
Is it possible to design a building as a flat plate system with a moment resisting frame, assuming lateral load will be carried by column only? There is no shear wall.
I lost something at the beginning. Is it possible to?
Design a building as a
Hmm.
flat plate system with a moment resisting frame, assuming lateral load will be carried by columns only. There is no shear wall.
Yeah, I didn't go there today. I did mention which day was it that we were doing
Yeah, this question,
flat,
similar question was asked before. So
flat plate. Okay, so I will repeat. This is an important question. If your seismic design category is D, then a flat plate column frame that does not have column line beams cannot be part of the seismic force resisting system, period. Okay. So the only way you can construct flat plate column frame for a design category D building is by combining the flat plate column frame with 100% seismic force resisting shear walls. However, if your design category is C or lower, then flat plate column frame can be part of the seismic force resisting system. Now you may, if you want, do without beams, without column line beams. Okay.
okay. What will be the attenuation of ground motion if there are multiple structures nearby? Will the ground motion reduce or it will remain same?
To the best of my knowledge, attenuation of ground motion does not depend on the structures that are around. It has to do with the the properties of the, what's the right, I don't know, the terrain, that the seismic motion is traveling along the surface of the earth. So the material close to the surface of the earth is going to dictate how quickly it dies down. Uh, Whether it is rock-like material or softer material, that kind of thing will make a difference. What structures stand nearby, I do not believe has a significant impact. I don't believe so.
Okay.
Yeah, I have never seen an attenuation relationship that stipulates that this is for urban areas and this and that. No, they don't consider the structures around.
Again, definition of dual frame system, questions related to that. Dr. Ghosh already covered these things in his presentation. So can you look at the recording once more? Two buildings of same height. One is bulky and wide structure and other is thin and slender. Then how the fundamental period of both the buildings is same?
Say that one more time.
Two buildings are of same height. One is bulky and wide structure and other is thin and slender. Then how the fundamental period of both the buildings are same?
The fundamental periods are not the same. The approximate period, which is a function of the height only, the approximate period would be the same. And when I teach this stuff, I always emphasize that the approximate period is not meant to be the real period of the structure. Its purpose is to get us started, and it also needs to be lower than the expected real period, because the lower the period, the more the higher the seismic design forces. So the answer to your question is the actual periods are not the same, but the approximate periods are the same.
Okay, so I will go to room 2 now. And there are two proposed buildings. One building, sorry,
Start again. To what?
proposed buildings.
Okay.
One of them is constructed in zone 2 and
Mm.
another is constructed in zone 3.
Mm-hmm.
But these two buildings are very close to each other. So
Mm-hmm.
my question is, can you consider different design parameter due to zone change, even though the buildings are very close to each other?
The answer is yes. You have to draw a line someplace, and you will do different things on different sides of the line, and that's how life is. You know, you you are on this side of the railway line or that side of the railway line. You know, life may be quite different, but you know that's how it is. The answer is yes. If you fall on the side of the line where the zone is 3, you will design for zone 3. If you fall on the side of the line that is zone 2, you will design for zone 2, and that's all there is to it. You cannot argue that I'm very close to 2, so I will design for 2, I'm not 3. No, that's not a valid argument. Then arguments erupt, you know, how close is close, you know. Do I have to be within 10 years, 100 years, half a mile, or, you know? So, no, you cannot go there.
Okay, Dr. Ghosh. So I think we replied most of the questions.
Okay.
Most of the questions were very fundamental, and like Dr. Ghosh covered that in length in his webinar today. So just watch the recording back, go through each and every slides that we have in our handout material, and you will find the answers there. And thank you so much for attending today's webinar. And next webinar is on, I think over the, I think it's on ethics, right, Dr. Ghosh?
Oh,
Next
is
one.
it? I don't know. I can look it up one second.
and it's on Saturday, 5th of February.
Let's see.
So
Yes,
according
your
to this,
5th of February, Engineer Hamid on ethics.
right,
Yeah. On Saturday, and on Sunday, Dr. Rakib on masonry.
right. So we will meet you on Saturday then for ethics webinar, and hopefully we'll see the same level of participation as today. And thank you so much. And I will open up the quiz in a couple of minutes. And thank you, Dr. Ghosh.
Thank you. Thanks. Thanks a lot.